Okay, welcome everyone. Welcome to the last day of the summary workshop of the INI program, Applicable Resurgent Asymptotics. We will have 4 talks today. And our first speaker is Shingo Kamimoto from Hiroshima University. And the title of the talk is Iterated Convolution and the Resurgence of Formal Solutions of Nonlinear ODEs. Please, Shingo.
Yes, thank you for introduction. And so, first of all, I'd like to thank the organizers for giving me this opportunity of my talk. So today, so I want to talk about iterated convolution and the resurgence of formal solutions of nonlinear ODEs. So let's start. So introduction. So as is well known, so especially for the participants of this seminar, so as is well known that so resurgence theory was initiated by Jean Ecart by his famous book. The title is The Resurgent Functions. Yes, in 1981, and so his theory is very powerful and very elegant, and so yes, very elegant. But so in the basic part of resurgent analysis, so there are some unclear things, especially about the analytic part of resurgent function theory is not so explicit in a sense, but so yes, but so especially so some of key estimate or key theorem in resurgence analysis was still unclear. So the purpose of this talk is to give a rigorous foundation of the resurgence theory, and the topics are the following 3 topics. So the first one is the structure of the space of resurgent functions. So yes, so resurgent function is defined by, I will explain as follows. But so, for example, so if we want to apply the theory to the analysis of resurgent analysis of nonlinear ODE, so we have to show the resurgence of the formal series or a resurgence of the solution. But so to show the resurgence, so for example, so we need some iteration method or something. To use iteration method, so of course we need some topology on the space of resurgent functions. And the first topic is about, in a sense, about the topology of the space of resurgent functions. And the next one is analytic continuation of the convolution product of resurgent functions. So yes, so nonlinear problem frequently appear in resurgent analysis, and of course, so the product of formal series is translated to the convolution product by the Borel transform. So analysis of the convolution product is very important in resurgent analysis. And so the next topic is about such problems, so analytic continuation of convolution product of resurgent functions. So especially, so we want to describe where the convolution product has a singular point in the Borel plane. And I will explain, I will give some explicit formula about the singularity structure of the convolution product. And the third topic is about the application to the nonlinear ODE. So we want to show resurgence of formal series solution of nonlinear ODE. And so in a sense, one of main purpose of my talk is to develop iteration method on the space of resurgent functions to show the resurgence of formal series solutions on nonlinear ODE. So before starting my talk, so I have to mention first that in these slides, result in works by David Sauzin and joint works with him is continuous. So fortunately, when I started studying resurgent analysis, so I could find his rigorous works and I could study by his works. And so in a sense, the result in this talk is variation or extension of his results. So anyway, let's start. So we first start from the definition of Borel transform. So maybe the participants of this seminar know well about the Borel transform, but to fix the notation, we start from the Borel Laplace resummation method. So the formal Borel transform is defined as written here. So in this way, we denote the formal Borel transform by V here. And so the formal Borel transform is a map from formal series in the variable x to here, C delta O plus C Guzai. So delta is correspond to a constant of formal series. So delta is a unit, and so it corresponds to 1 in the formal series Cx. And so by applying the Borel transform, so we write in this way. So phi 0 is the constant term of the formal series phi x, and phi hat Guzai is the Borel transform of remainder term, remainder part. And so phi hat Guzai is defined in this way as usual. So by dividing j minus 1 factorial, by dividing each coefficient by j minus 1 factorial, and in this ways. And so if phi x is Jubilee order 1, so that means if there exists positive constant C and A such that for all j greater than or equal to 0, so the coefficient phi j satisfies this estimate, then we say Jubilee order 1. And so in this case, phi hat Guzai. So the part here, phi hat Guzai, defines analytic jam at Guzai equals 0 because phi hat Guzai is convergent series in this case. And so in this way, we define a formal Borel transform. And next, the Borel sum, the definition of Borel sum. So when phi hat Guzai is convergent at Guzai equals 0 and analytically continued to the sector SD alpha, this one. So the center is direction, the center of the direction is D, and the opening is alpha here. And we denote it by SD alpha. And also, phi hat Guzai satisfies this estimate on the sector for some positive constants C and H. Then we say that phi x is Borel summable in the direction D. Then the Borel sum SD phi is defined by the Laplace transform LD as follows. So in this way. So using this Borel sum, we define the Borel sum by first applying the Borel transform here, and next the Laplace transform here, and we obtain a function SD phi when the formal series phi x is Borel summable in the direction D. So the Borel summation. So when phi x is Borel summable in D, then the Borel sum phi d SD pi x defines analytic function on the sector here. And the Borel sum SD phi is asymptotic to pi x. So in this way, so we start from formal series here, but by taking Borel sums, so when phi x is Borel summable, we can obtain analytic function by taking Borel sum, and it gives yes. So as an asymptotic expansion, so pi x is given by pi SD pi x. But so if the correspondence is complete or works well, so there is no problem. But so we assume that the phi x is Borel summable indeed. But if phi x is not Borel summable, so some problem occurs at the direction. And the problem is so-called Stokes phenomena. So in a sense, we can say that the difference between formal structure and analytic structure is described by Stokes structure. And so in a sense, so we can say that Stokes phenomena occurs as a gap between these two structure, formal structure and analytic structure. And for example, so yes, Stokes phenomena is important to analyze the structure of differential equation at a singular point. And so Stokes phenomena or Stokes structure is very important object in the analysis of differential equation. So we want to analyze Stokes phenomena. And so one of the advantage of resurgent analysis or Borel resummation, Borel Laplace resummation method is the following. So by applying the Borel transform, Stokes structure is translated to the singularity structure of pi hat xi in the Borel plane. So in this way, so in a sense, Stokes structure is a little difficult to analyze directly. But so using Borel transform, so we can translate the structure to the singularity structure of pi hat xi in the Borel plane. And so our analysis is translated to the singularity structure in the Borel plane. And so in this talk, so we focus on the analysis of formal series solution in the Borel plane. So I mean, so yes, the Borel transform of formal series solution of the following nonlinear ODE. So we want to analyze the singularity structure of pi hat xi. So here pi is the formal series solution of this nonlinear ODE. Yes. So yes, so this is the main purpose of this talk. So now we mentioned here alien operators. So I want to explain alien operator a little bit. So let omega r be the singular points of pi hat on the ray r ei theta. And so we assume that so pi hat has a singular point. So here is a picture, and so this picture corresponds to theta equal to 0. And so in this case, so we assume that singular point appears on the positive real axis. And so all the singular points is exhausted by omega 1, omega 2, omega 3, or omega 4, and the rest. So we assume that. And so in this situation, the Stokes operator is defined by in this way. So, and here omega, so delta omega r plus is operator defined in this way. So first, so the path here gamma plus 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 means a path like this. So it starts from here. So So like this. So when r equal to 3, then here the path is gamma plus plus, and so gamma plus plus denotes the path written here. So avoiding first singular point omega 1 from the right hand side, and the next singular point omega 2, we also avoid the singular point from the right hand side and go to the singular point at xi equal omega 3, and taking the singular point at omega of phi hat omega 3 is yes, the operator means so yes this. And so in this way, so we define delta omega r plus, and using this operator, so Stokes operator is defined in this way. And the infinitesimal Stokes operator is defined in this way here, and it corresponds to the logarithm of Stokes operator delta plus. And so by combinatorial calculation, so we can show that delta is the logarithm of delta plus. But anyway, so delta is defined in this way. And here the path gamma epsilon corresponds to this path here. So here as an example, so the path gamma minus plus minus is written here. So minus sign means so avoiding the first singular point from left hand side, and plus sign here. So plus sign means so is avoiding the singular point, next singular point omega 2 from the right hand side, and third singular point from the left hand side, and going to the singular point at xi equal omega 4, and taking the singular point at omega 4. So this is the operator here. And the number here p epsilon is the number of positive sign in the epsilon, and q epsilon is the number of minus sign in epsilon. And in this way, so infinitesimal Stokes operator is defined. And so here, so one of the important point here is that so this operator delta omega r is derivation, and so it behaves very well. And so because so this operator is derivation, so this operator is called alien derivative. And so alien derivative is one of the important tool, important tool in the resurgent analysis, and but so it contains analytical continuation along gamma epsilon. So it is a global operator in the Borel plane. But so the problem is, so when we can define alien operators, or so what kind of function so we can define alien operator, alien derivative. So the problem is, yes, as I said, so when we can define, well, what kind of function space we can define alien operator. So because, so as I said, so it contains global analytical continuation along so this kind of path. So in this way, so one of the tool contains global analytical continuation. So we need some global analysis in the Borel plane. And so, and for example, so another problem is, for example, so what kind of singular point appear in the Borel plane when we analyze a differential operator, or for example, difference operator. So the problem is, this kind of problem appears in the resurgent analysis. And one of the answers to the question, so Jean et al. Introduced the notion of endlessly continuable function. So so I will explain endlessly continuable function here. So the notion of endlessly continuable function was introduced by Jean Ecart to describe the singularity structure in the Borel plane of resurgent functions. And so, in this talk, so we follow the definition given by Kandelberger, Nosmas, Pham. So, so in his book, in their books, so they introduced the following definition of endlessly continuable function. So definition here. So let pi be the set of Lipschitz continuous paths gamma. So the parameter is 0 to 1 to the complex plane, satisfying gamma 0 equal to 0. Then we say an analytic germ pi hat guzai is endlessly continuable if for any positive constant L, there exists a finite set FL in complex plane such that pi hat guzai is analytically continuable along any path gamma in pi with a length less than L, satisfying this condition. And the set of endlessly continuable function is denoted by R hat. So it means this parameter L represents the length of the path we are considering, and if the path is less than the length of the path is less than L, then also the path is satisfy this condition. So this means the path path avoids a singular point described by the finite set FL, then pi hat is analytically continuable along the path gamma, then we say the function is endlessly continuable. So in a sense, we say that in a sense, this definition says that pi hat may have a singular point very much, but the singular point must appear finitely many if we restrict finite length of the path. But this definition does not by this definition, we cannot say that pi hat does not has many singular points. So I mean, endlessly continuable function may have singular point density in complex plane. So this function may have singular point density in complex plane. So this is the problem, because if the function has singular point density in complex plane, so the analysis becomes very complicated. But this kind of functions appear in the analysis of differential equation. So we define endlessly continuable function in this way, but we actually face this kind of situation when we analyze a differential equation. Using the endlessly continuable function, resurgent function is defined in this way. So an element in C delta O plus R hat is called resurgent function, and formal series phi x is called resurgent formal series if phi hat guzai in R hat, and the set of resurgent formal series is denoted by R. And by the definition, we have the following isomorphism. So applying the Borel transform to an element in R, then it is in here. And it follows by the definition of R. So anyway, okay, so I introduced the definition of endlessly continuable function, but So it is not easy to handle endlessly continuable function directly, because yes, when we say endlessly continuable function, so that singular point is not specified. But so when we discuss, for example, the location of a singular point or something, so we have to describe or specify the singular point the function may have. And yes, so for that purpose, so we introduce a discrete filtered set. So we use discrete filtered set introduced by the book, by them, and to describe final singularity structure in the Borel plane. So discrete filtered set is defined in this way. So a family omega of subsets in C is called, if it satisfies, called discrete filtered set if it satisfies the following conditions. So omega L for each L is a finite set, and omega L1 is contained in omega L2, and it holds for any L1 less or equal to L2. And the third condition is there exists some positive constant delta such that omega delta equal to empty set. So the first condition means that singular point. So we want to describe the singular point of endlessly continuable function by using discrete filtered set, and the first condition guarantees that singular point may appear, but appears finitely many if we restrict the analytical the length of analytical continuation. The length of the path of analytical continuation is less or equal to L, less than or equal to L. And next condition is says that singular point may appear when we analytically continue further and further. And the third condition guarantees that so we start from analytic jam at the origin. So the third condition guarantees that the function we are considering is analytic at the origin. And so for discrete filtered, we define discrete filtered set in this way. And for discrete filtered set omega, so we set S omega here and M omega. And here S bar omega denotes the closure of S omega in R non-negative times C. And so in a sense, so here S omega describes the singular points described by discrete filtered set omega, and M omega is M omega is or M omega is obtained by eliminating singular point from entire space here. And we introduce S omega and M omega in this way. And now, so we define omega continuability of the function. So we say that a path gamma in pi, so Lipschitz continuous path gamma is omega allowed if gamma tilde t. So here L gamma sub t is the length of the path gamma t here. Gamma t denotes the restriction of gamma to the interval 0 t. And yes, gamma t is the path here. And if gamma tilde t is in omega M omega, then the gamma tilde t avoids the singular point described by discrete filtered set omega. Then we set the path gamma is omega allowed, and the set of omega allowed paths is denoted by pi omega. And using omega allowed paths, so we define omega continuability in the following ways. So an analytic jam phi hat Guzai is omega continuable if pi hat xi is analytically continuable along any path gamma in pi omega. And the set of omega continuable function is denoted by r hat omega. So it means, so if the analytic germ is continuable along any path that avoids a singular point described by discrete filtered set omega, then we set the analytic germ omega continuable. And we define omega continuability for a discrete filtered set omega in this way. And as in the case of resurgent function, so we define omega resurgence of omega resurgent function in this way. So an element in C delta O plus R hat omega is called omega resurgent function. And a formal series pi x is called omega resurgent formal series if pi hat xi in R hat omega. And the set of omega resurgent formal series is denoted by R omega. And by the definition, so we have the following isomorphism. So here, and so it follows by the definition. So in this way, so we define omega resurgence for a discrete filtered set omega. And so let us consider an example given here. So let omega L, omega be a discrete filtered set defined by, so this formula here. So then, for example, so this function is omega continuable because so this function looks that so it has a singular point at xi equals 0, but so this integration starts from the origin 0, so it is analytic at the origin. So pi hat xi is analytic at the origin. But so this integrand here has a singular point at xi equal to 1. So here it appears, so omega L, so if L is greater than or equal to 1, so omega L contains 1. So it represents a singular point at xi equal 1 of the singular of the function pi hat xi. And so in this way, so it has a singular point xi equal 1, but the problem is the following. So if we go analytical continues along the path in this way, and for example, so if we avoid the singular point at xi equal to 1 from the right hand side and turn around the singular point here, and if we return to the origin, so the branch of this integration becomes a different one. So since it has a factor xi 1 over xi, so this function has a singular point at xi equal to 1, and so omega L must contain xi equal to 0 when L is greater than or equal to 2. And in this way, so we can describe the singularity structure or seat structure of pi hat xi using a discrete filter set in this way. And so we can say so pi hat xi is omega continuable. So next example is, so this is a prototype of our following discussion. So let sigma be a closed discrete set in complex plane, satisfying that so 0 is not contained in sigma. And we define discrete filtered set omega sigma associated with this set sigma by this formula. So if if an element omega in sigma, and yes, the absolute value of omega is less than or equal to L, so it contained in omega sigma L. And in this way, we define a discrete filtered set from sigma. And then gamma is omega sigma allowed if and only if gamma satisfies this condition. So gamma avoids the point in sigma. Then so we say so gamma is omega sigma allowed. And so therefore pi hat Guzai analytic jam is omega sigma continuable if and only if pi hat Guzai is analytically continuable to the universal covering space. We denote by x omega sigma of C minus sigma. And hence we have the following isomorphism. So we defined an element in R hat omega R hat omega sigma by the analytical continuability of the functions. But we can represent such functions by as the global section of O x omega sigma on x omega sigma. So here, so O x omega sigma denotes the sheaf of holomorphic functions on x omega sigma. And then, so R hat omega sigma becomes Frechet space with the seminorms. So here, K is a compact set in x omega sigma. So in this way, so if the discrete filtered set is given by a closed discrete set in complex plane, so in this way, so we can introduce Frechet space structure in this way. So using compact set in x omega sigma. And so as I said, so this is a prototype of our following discussion. So in this way, so we can introduce topology on the space of R hat omega sigma. But so to introduce topology or seminorms in this way, so we need so Riemann surface. So we need Riemann surface x omega sigma. So in this way, so it is given by the universal covering space of C minus sigma, but we want to construct this kind of Riemann surface for general discrete filtered set omega. So for that purpose, we introduce omega endless Riemann surface. So omega endless Riemann surface is defined in this way. So let X be a connected Riemann surface with a point on X, specified point on X, and so we denote it by 0 underbar. And let P a pair be a locally biholomorphic map from X to complex plane C, satisfying that the condition here. So then we say that the triplet X pair 0 underbar is omega endless Riemann surface if it satisfies the following conditions. So for any gamma in pi omega, so for any omega endless, omega allowed path gamma, there exists a path gamma bar. So it is a lift of gamma to the Riemann surface X, satisfying this condition and this condition. So it guarantees, so this gamma underbar is a lift of the path gamma. And so if the condition holds, so we say that xp 0 underbar is omega endless Riemann surface. And morphism q from x pair 0 underbar to x prime pair prime 0 prime underbar of omega endless Riemann surfaces is a locally biholomorphic map Q, such that the following diagram is commutative. So if biholomorphic map, a locally biholomorphic map Q is given here, and if the diagram here is commutative, then we say that the morphism Q is a morphism of omega endless Riemann surfaces. So in this way, so we introduce omega endless Riemann surface. And so we introduced omega endless Riemann surfaces, but the most important one is the initial object in the category of omega endless Riemann surfaces. So that is the most important one, because the existence of the initial object is guaranteed by this theorem. So it is obtained by joint work with David Sauzin. So there exists a simply connected omega endless Riemann surface. So we denote it by x omega, p omega, 0 underbar omega, such that for any omega endless Riemann surface, x, p, 0 underbar, there exists a unique morphism Q, this one. And so the important point of this theorem is that, so this theorem indicates that x omega, p omega, 0 underbar omega has the finest seat structure among omega endless Riemann surfaces. So initial object gives the finest seat structure. And so we can show that such an initial object exists and it has the finest seat structure among the omega endless Riemann surfaces. And for example, so it is an extension of universal covering space of C minus sigma in the case, so sigma is given by closed discrete set here. Yes, so x omega sigma coincide with the universal covering space of C minus sigma. And so in a sense, so this omega endless Riemann surface is an extension of universal covering space. And so we can construct this Riemann surface for a general discrete filtered set omega. And so using this omega endless Riemann surface, so we have the following isomorphism. So for any discrete filtered set omega, so we have the isomorphism. So any omega continuable function is represented as a global section over x omega of holomorphic, the shape of holomorphic functions. So we can represent omega continuable function by as the global section on x omega of holomorphic function of the shape of holomorphic functions. And using the representation of r hat omega, so we can introduce a structure of Fresh space on r hat omega determined by the seminorms. So this one for compact subsets K of x omega. And so we have the isomorphism given by Borel transform here. And so it also defines a topology on R omega resurgent, the space of omega resurgent series. So in this way, so using omega, the initial object of the category of omega endless Riemann surfaces, we can introduce topology on omega endless on the space of omega endless omega continuable functions r hat omega. So in this way, so we can introduce a topology on r hat omega. So now, so we explain a little about a comparison of discrete filtered set. So let omega and omega prime be discrete filtered sets, and when omega L is contains omega prime L for any L, non-negative L, so we write omega is contained in omega prime, and then by the definition, so we have the following relations for pi omega, r hat omega, and r omega. And so further, since the omega endless Riemann surface x omega, p omega, 0 underbar omega is omega prime endless in this case, so there exists a morphism of omega prime endless Riemann surfaces. So in this way. And so we first introduced endlessly continuable functions. and we denoted it, denoted the space of omega endlessly, we denoted the space of endlessly continuable functions by R hat. But so in this way, so R hat is written by the union of R hat omega for all discrete filtered sets omega. And so in this way, so the space of endlessly continuable functions is exhausted by omega continuable functions. And so in a sense, so yes, so in this way, so we can represent for any endlessly continuable function by some some using some discrete filter set. So we can write omega omega continuable function. So now, so let us consider next convolution product of functions. So as you know, so the Borel transform translate the product in CX to the convolution product, and the convolution product is written using star. And so when phi hat xi and psi hat xi is analytic germ at the origin, then so the convolution product is given by using this integration. And so as I said, so the product in CX is translated to convolution products. So it is important in the analysis on the Borel plane to know how the singularity structure of phi hat star psi hat is determined by that of phi hat and psi hat. So it is especially, so it is very important when we discuss nonlinear problem. So we want to consider this problem. So analysis along a line. So this is very standard techniques or standard discussion. So we can discuss very easily analytic continuation along a line. So I skip here. But when we want to discuss analytic continuation along a curve, so we encounter some problem. So let us consider phi hat xi is given by this one, and psi hat xi is given this one, given by this one. And so it has a singular point at omega 1 and omega 2. And the convolution product of them is, by definition, is written in this way. But if we rewrite, this one, so we can rewrite it in this way. So if we look this representation, so it has a singular point at xi at equal omega 1 plus omega 2 here, and omega 2 and omega 1. But of course, so if we go directly from the origin to the point omega 1 plus omega 2, no singular point appears because these two functions, phi hat and psi hat, is analytic along the line. So the convolution product must be analytic along the line. So this representation says that it has a singular point. If we go avoiding singular point, for example, omega 1 from the right hand side and go to omega 1 plus omega 2, then so it has a singular point omega 1 plus omega 2. And so when we consider convolution product of resurgent functions, so this kind of seat structure frequently appears. And so we must describe this kind of seat structure, effectively. And so one of the purposes of introducing discrete filtered set is to describe this kind of seat structure of convolution product of resurgent functions. So we now define the sum of discrete filtered sets, and it represents the singular point of convolution product of omega continuable functions and omega prime continuable functions. So for given two discrete filtered set omega and omega prime, so we define the sum omega star omega prime by the formula here. And we write omega star n times sum of omega, and omega star infinity is the inductive limit of omega star n. So since omega star n consists inductive system, so we can define inductive limit. We can take inductive limit of omega star n, and we can confirm that omega star infinity also defines a discrete filtered set. And by the definitions, so for m and n, so we have this relation. And so in the previous example, so we see that phi hat is in r hat omega 1, and psi hat is in r hat omega 2, and the convolution product is here. And the seat structure of the convolution product described effectively by using the sum of discrete filtered sets in this way. So now let us discuss analytic continuation of convolution product. So it is proved by David Sauzin for the case of the singular point is given by closed discrete set, and it is proved by O and Delaval in the case that omega is given by discrete filtered set. And so the theorem says, if given omega and omega prime, and if phi hat is omega continuable and psi hat is omega prime continuable, then the convolution product is omega star omega prime continuable. And in this way, so we can describe the singularity structure of the convolution product here using the sum of discrete filtered set. So to discuss analytic continuation, we use gamma adapted symmetric homotopy. So the definition of symmetric omega homotopy is here. And so using omega symmetric omega homotopy, so we can give analytic continuation of convolution product in this way. But I have no time to explain precisely about symmetric omega homotopy, so we skip here. But anyway, extending the definition of symmetric omega homotopy, so we can show the following estimate for convolution product. So in the case of given by obtained by David Sauzin and I. So in the case, the singular point is given by closed discrete set. So this result is obtained by David Sauzin, and we extended the theorem to the case of omega discrete filtered set case. And so we have the following estimate for the convolution product phi 1 hat star delta phi n hat, and so the supremum on the compact set K is given by estimated by this one. And important point here is the order of the statement here and here. So if we fix first compact subset K, then for any so we can take compact subset K prime and constant C independently of natural number n and the function phi 1 hat to phi n hat. Sorry, here. And so we can take k prime and c uniformly for n and the function phi 1 hat to phi n hat. So using this estimate, so we can show the convergence of substitution of f by omega resurgent series is convergent and it is omega star infinity. So now I want to explain about application to the differential equation, but so unfortunately I don't have time, so I skip here. So one of the main result is this one. So using a discrete filtered set given by this sigma, and then so sigma is determined by eigenvalues of linear part of the equation, linear part of this one. Then so we can show that formal series phi x is omega sigma star infinite resurgent. So we can show that the singular point of a Borel transform of this formal solution phi x is generated by the singular point at the eigenvalues of linear part del pi f. And in this way, so we can show the resurgence of formal series solution of this nonlinear ODE. So it's time, so I stop here. Thank you for your attention.
Thank you very much for the nice talk. So it's time for questions or comments. Yes, Ovidio has a question.
Right. Yeah, I mean, it's more of a comment that in the context of this nonlinear ODE's resurgence of formal series of trans-series medianization, École calculus, were analyzed in my Duke Math Journal paper by a different method. I mean, convolution algebras of distributions. And I think it would be interesting to compare the methods and results. More of a comment. The different methods may have their advantages and whatnot. And I would suggest that maybe we arrange a Zoom meeting later in the summer with David and with you to sort of chat about these issues. Yeah. That's what I had to say.
Thank you. Yes, David?
Yes, to add further to Ovidio's comment, I agree it would be interesting to compare the results because there was this question about the role of the sums of eigenvalues. We have the statement still on this, and we see that in Shingo's result, it's not only the eigenvalues themselves and their multiples, but it's also the sums of multiples, which will, because you see this omega sigma star infinite, it means that you start by building a discrete filter set. So you have, well, in that case, you start with a finite set, so it's not a big deal. But then omega sigma star 2, star 3, it means you authorize sums of 2 elements or 3 elements, and so you end up with a pretty rich set of singularities.
Right,
and I have a question.
Yeah.
And I have a question to Shingo. I haven't seen the full proof of your theorem. So my question is, have you a preprint to that end, Shingo?
Huh?
Have you a
Yes.
preprint or a published article for that theorem?
Yes.
I think I have read an announcement. I know of an announcement, a note announcing the result. But so my question is simply: is the full proof published or available?
Yes, it is uploaded to archive.
Oh,
Full
thank
proof
you.
is uploaded to archive. Yes. So I
Thank
think
you.
I sent to announcement, but so full proof is also uploaded to archive. Yeah.
Thank you. I'll check that. Thank you.
Right. So as a comment to the comment, so all these structures, yes. So it follows actually from a Carl-Sagan calculus, because the sort of and some sort of as I use it in my Duke marginal paper, is some sort of a Riemann-Hilbert problem. So you have the jump across the cut of one of the elements of the series, say the first series. This given as sort of the next term in the trans-series, but then on its first Riemann surface. And it's through these combinations of sort of continuations that we get the whole Riemann surface of each of them. But that's in the framework of ODEs. So you need this kind of the alien calculus of a call, in my paper at least. So that partly answers your question, but I would really be interested to discuss and sort of see exactly. Your method does not require any extra structures. It's the general sort of position of singularities generated by a convolution of any kind of a problem. I mean, it could be an ODE, a PD, a difference equation, or even without this structure. So they are a bit of different animals, and yeah, I mean, it requires a discussion. I mean, all right.
Okay, I may have one question. So is your theorem on the convolution, so could it be useful for WKB analysis as well? So by
Yes,
constructing the WKB solutions through Riccati equation, then you have to take convolutions as you construct the.
Yeah, but so when we solve, for example, Riccati equation, so we need one more operation to solve first order PDE. So it is, yeah. So my theory describes the singularity structure of convolution product. But so when we consider, for example, Riccati equation, so we need one more theory to describe a singular point solving by first order ODE, PDE. So maybe we can apply the theory to the Riccati case, but we need some discussion. Yeah.
Is it because of the mixture between the two variables, like the Borel variable and the independent variable are mixed up in the integral equation?
Yeah.
I guess that makes it harder. Thank you.